Every astronaut knows this terrifying fact. Space has over 1,000 ways to kill you, and most of them happen within the first minute. The vacuum will boil your bodily fluids, cosmic radiation will fry your DNA, and temperatures swing from 250 degrees Fahrenheit in sunlight to negative 250 degrees Fahrenheit in shadow. Yet, in 2025, we've built spacesuits so sophisticated, they're basically wearable spaceships. These aren't the bulky white suits you remember. Modern designs are sleek, smart, and packed with technology that would make science fiction writers jealous. But here's what most people don't realize about how they actually keep you alive in an environment that remains as hostile as ever. The deadly reality of space in 2025. Despite all our advances in rocket technology and spacecraft design, space itself hasn't gotten any friendlier. The same 5 killers that threatened Yuri Gagarin in 1961 are waiting for today's astronauts with the same lethal efficiency. Understanding these threats reveals why modern spacesuits represent some of the most complex engineering ever attempted by humans. First comes oxygen deprivation, the most immediate threat. Your body stores roughly 4 minutes of oxygen in your bloodstream and tissues. Without a pressurized oxygen supply, you'll lose consciousness in 15 seconds as the oxygen in your blood gets used up and carbon dioxide builds to toxic levels. Brain death follows within 4 to 6 minutes. There's no gradual decline, no dramatic gasping for air like in the movies. Your vision narrows, your thinking becomes fuzzy, and then you're gone. The pressure differential presents an equally deadly challenge. Earth's atmosphere presses against your body with 14.7 pounds per square inch. This pressure keeps your bodily fluids in their liquid state and maintains the proper function of your organs. In the vacuum of space, this pressure vanishes instantly. Bodily fluids begin to vaporize within 10 to 15 seconds. The moisture in your lungs will expand rapidly, and your blood won't boil immediately because your circulatory system maintains some internal pressure. But within 30 seconds, nitrogen dissolved in your bloodstream will form bubbles, causing decompression sickness and organ swelling that can kill you even if you're rescued. Temperature extremes create the third major threat. When sunlight hits you directly in space, temperatures reach 250 degrees Fahrenheit. Your skin would suffer severe burns within minutes, and your internal organs would begin cooking as your body's cooling systems fail completely. In Earth's shadow, temperatures plummet to negative 250 degrees Fahrenheit. Without the insulation of an atmosphere, your body heat radiates away rapidly, causing hypothermia that would kill you within hours even if you somehow survive the other threats. Cosmic radiation forms an invisible but constant danger. High-energy particles from dying stars and solar flares bombard anything in space with radiation levels hundreds of times higher than what we experience on Earth. A single large solar particle event can deliver a lethal dose of radiation in minutes. Even the constant background radiation will damage your DNA, increasing cancer risk and causing radiation sickness during extended exposure. Your body has no natural defense against these high-energy particles that pass through normal matter like it doesn't exist. Micrometeorite impacts represent the fifth threat. Tiny particles traveling at speeds up to 45,000 miles per hour. A fragment smaller than a grain of sand carries enough kinetic energy to punch through human tissue like a bullet. The International Space Station gets hit by objects this size regularly, requiring constant repairs to solar panels and exterior surfaces. A single impact to an unprotected human body would cause massive trauma and rapid death from blood loss and organ damage. The margin for error remains absolutely zero. A pinhole leak in a suit's pressure vessel will kill you in minutes. A failure in the oxygen supply system means death within the time it takes to recognize the problem. A malfunction in the cooling system during sunlight exposure will cause fatal hyperthermia before ground control can even respond to your distress call. A breach in radiation shielding during a solar particle event delivers doses that cause death within days or weeks. This zero tolerance for failure explains why modern spacesuit development has become so incredibly complex. Engineers must create systems that work perfectly in an environment that destroys everything. Every component must function reliably while exposed to temperature swings of 500 degrees, radiation that would kill unprotected electronics, and the constant threat of high-velocity impacts. The suits must maintain perfect pressure integrity while allowing enough flexibility for complex manual tasks. They must provide life support for 8 hours or more, while remaining light enough for astronauts to move effectively. Modern spacesuit engineering has achieved something that borders on the impossible, creating a portable life support system that can keep humans alive in an environment designed to kill them instantly. These suits must function as personal spacecraft, complete with life support, communication systems, radiation shielding, and impact protection. They represent the culmination of 60 years of learning from failures, near misses, and the constant refinement of systems where anything less than perfection means death. But this sophisticated technology didn't appear overnight. The journey from our first attempts at space protection to today's advanced systems tells a story of desperate innovation and life or death problem solving. From Mercury to Artemis, the evolution story. The first spacesuits were essentially modified high-altitude pilot suits with some extra engineering attached. Engineers in the late 1950s took flight gear designed for military pilots and adapted them for the complete vacuum of space. Mercury suits recycled breathing gas, but weren't designed for spacewalks. These early designs were worn inside spacecraft capsules and proved that humans could survive spaceflight, but they also revealed the enormous challenges ahead. The Gemini program from 1961 to 1966 forced engineers to solve the problem of spacewalks for the first time. Gemini suits included umbilical connections to the spacecraft that provided oxygen, power, and communication links during extravehicular activities. These tethered systems allowed astronauts to leave their capsules, but the umbilical cords limited their range and created new safety risks. Ed White's first American spacewalk in 1965 nearly ended in disaster when his suit overheated and his visor began fogging up from excessive moisture. This near catastrophe drove engineers to develop better cooling systems and revealed that spacewalking required completely different engineering approaches than simply surviving inside a pressurized capsule. Apollo program suits represented the first major engineering breakthrough in space suit design. These suits had to protect astronauts walking on the lunar surface while dealing with abrasive dust, sharp rocks, and micrometeorite impacts. Apollo suits featured built-in life support systems that eliminated the need for umbilical connections to spacecraft. This portable life support backpack provided oxygen, removed carbon dioxide, and regulated temperature for up to 8 hours of continuous operation using pure oxygen at about 3.7 psi. The lunar environment created unique challenges that drove specific innovations. Moon dust proved incredibly abrasive and got into every crevice, threatening to damage seals and moving parts. Engineers developed special boot designs with thick soles that could handle walking across rough terrain covered in fine, sharp particles. The suits included multiple layers of protection with an outer shell designed to resist tears and punctures from sharp lunar rocks. Apollo engineers solved the seemingly impossible problem of creating flexible joints that could maintain pressure while allowing natural movement, using innovative bearing systems that reduced the energy required for movement while maintaining structural integrity. The space shuttle era brought a completely different approach, focusing on modular components that could accommodate multiple astronauts rather than custom-fitted individual suits. This shift towards standardized sizing created cost savings, but introduced new problems with fit and comfort. The modular approach sometimes created fit problems that led to injuries, particularly hand and shoulder problems from poorly fitting components. However, shuttle suits also introduced significant improvements in mobility and tool integration, featuring better joint designs that reduced fatigue during long spacewalks and improved glove systems that enhanced manual dexterity. Each generation of suits had to overcome limitations that nearly killed astronauts during actual missions. Mercury suits couldn't handle vacuum exposure, Gemini suits overheated and created mobility problems, and early Apollo prototypes failed pressure tests that would have been fatal in space. Shuttle suits caused injuries from poor fits and joint problems that accumulated over multiple missions. These failures drove continuous improvements in materials, joint design, life support systems, and manufacturing techniques. Current spacesuit development represents the biggest revolution in design since the Apollo program. Modern suits must handle multiple mission types simultaneously, from International Space Station operations to lunar surface exploration to potential Mars missions. Engineers are incorporating smart materials that can monitor suit integrity and astronaut health in real time. Artificial intelligence systems now assist with life support management and predictive maintenance. Advanced manufacturing techniques allow for better custom fitting while maintaining modular designs. Today's suit designers face challenges that previous generations couldn't imagine. Extended missions to Mars will require suits that can function reliably for years without major maintenance or replacement. Lunar base operations need suits that can handle repeated exposure to abrasive dust and extreme temperature cycles. Commercial space operations require suits that work with multiple different spacecraft designs and operational procedures. Deep space missions will expose astronauts to radiation levels and micrometeorite risks, far beyond anything experienced in Earth orbit. The engineering requirements for future suits exceed anything attempted before. Mars surface operations will require suits that can handle dust storms, temperature variations, and extended surface operations lasting months. Deep space missions need radiation shielding that doesn't compromise mobility or add excessive weight. Asteroid mining operations will require suits that can handle sharp, abrasive materials and complex industrial tasks in zero-gravity environments. This evolution from basic pressure suits to sophisticated life support systems has reached a critical turning point. The next generation of spacesuits must function as something far more advanced than anything previously attempted, incorporating decades of lessons learned from every near disaster and engineering breakthrough that came before. NASA's XEMU, the Artemis game changer. NASA's XEMU suits represent the culmination of this engineering evolution, functioning as personal spacecraft with independent life support, communication systems, and navigation equipment that can keep astronauts alive on the lunar surface for up to 8 hours without any connection to a base or rover. These suits incorporate redundant systems that eliminate single points of failure and smart monitoring that can predict problems before they become dangerous. The design philosophy centers around building the spacecraft around the astronaut rather than fitting the astronaut into existing equipment. The Artemis program drives every aspect of XEMU development, from the suit's ability to handle lunar dust to its enhanced mobility systems designed for partial gravity environments. Unlike previous lunar missions that lasted only a few days, Artemis crews will establish a permanent presence at the lunar South Pole, requiring suits that can handle repeated exposure to extreme conditions and extended surface operations. The XEMU must function reliably during multiple EVAs per week over mission durations lasting months rather than the short Apollo visits of the 1970s. The most revolutionary advancement lies in the XEMU's joint design, which uses advanced ball bearings and materials that maintain pressure integrity while providing smooth, natural movement. These enhanced joint bearings at the hips, knees, and ankles enable bending and rotating movements that previous suits couldn't accommodate. Astronauts can now kneel down to collect samples, climb over rocks, and perform complex manual tasks without the exhausting struggle against suit stiffness that characterized earlier designs. The enhanced flexibility reduces energy expenditure by 40% compared to current International Space Station suits, allowing longer work periods and reducing injury risk from repetitive strain. Each joint incorporates multiple layers of protection against dust infiltration, a critical concern for lunar operations where abrasive particles can damage moving parts. Engineers developed special seals and covers that prevent lunar dust from jamming joint mechanisms while maintaining the flexibility needed for complex tasks. These mobility improvements directly translate to improved scientific productivity and safer operations during extended lunar surface missions. The second major innovation involves integrated life support monitoring systems that can sustain astronauts for extended periods through sophisticated atmospheric management and thermal regulation. The primary life support system monitors and adjusts oxygen levels, carbon dioxide removal, temperature, and humidity automatically while providing real-time feedback to both the astronaut and mission control. Advanced sensors throughout the suit monitor everything from oxygen partial pressure to suit integrity, detecting micrometeorite impacts or seal degradation before they become dangerous. The life support system can operate in multiple modes depending on activity level and environmental conditions, optimizing resource consumption during low activity periods and providing maximum support during strenuous work. The XEMU's modular design allows customization for different mission requirements and easier maintenance than any previous suit. Suit segments can be swapped or modified based on specific mission needs, accommodating different body sizes and operational requirements. This modularity enables the suit to fit at least 90% of the male and female population, eliminating the custom fitting requirements that limited previous programs. The same basic suit can be configured for lunar surface operations, spacecraft-based EVAs, or emergency situations by swapping specific components. The lunar South Pole presents unique challenges that drove specific XEMU design features. Permanently shadowed regions maintain temperatures as low as negative 414 degrees Fahrenheit, requiring specialized thermal protection and heating systems. The suits include insulated boots with heating elements and advanced thermal regulation that can handle extreme temperature gradients when astronauts move between sunlit and shadowed areas. Helmet-mounted headlamps provide illumination in the perpetual darkness of crater floors where water ice deposits await collection. Communication and navigation systems built into the XEMU eliminate the need for separate equipment while providing capabilities that exceed current International Space Station standards. The integrated audio system uses internal loudspeakers and digital microphones to provide clear communication without traditional headsets that can cause discomfort during extended wear. Helmet-mounted heads-up displays provide real-time information about suit status, navigation data, and mission timelines without requiring astronauts to look away from their work. Decades of spacewalk experience directly influenced XEMU design decisions, addressing problems that accumulated over hundreds of EVAs. The suit eliminates pressure points that caused injuries during long spacewalks and incorporates ergonomic improvements that reduce fatigue and strain. Advanced glove designs provide better dexterity while maintaining pressure integrity, addressing one of the most persistent problems with previous suit generations. Current testing programs validate XEMU performance under extreme conditions that simulate lunar operations. NASA's Citadel chamber subjects suit components to temperatures as low as negative 248 degrees Celsius while using simulated moon regolith to test how boots and gloves perform under authentic lunar conditions. These tests use synthetic hands and feet with fluid circulation systems that replicate warm blood flow, while dozens of sensors measure temperature and heat transfer throughout the components. The suits must demonstrate perfect performance during simulated lunar surface operations that include exposure to temperature extremes, abrasive dust, and the complex tasks required for scientific research and base construction. These validation programs ensure that XEMU suits will enable the extended lunar missions that form the foundation of humanity's permanent expansion beyond Earth. But while NASA perfected the engineering approach to spacesuit design, another company was preparing to challenge every assumption about what a spacesuit should look like. SpaceX's sleek revolution. SpaceX shattered every assumption about spacesuit design when they unveiled suits that look like they belong in a science fiction movie rather than a NASA laboratory. While traditional spacesuits resemble puffy white marshmallows that transform astronauts into slow-moving robots, SpaceX created form-fitting black and white suits that make astronauts look like superheroes preparing for battle. This radical departure from conventional design represents more than just aesthetic choices. It reflects a completely different engineering philosophy that prioritizes integration, manufacturing efficiency, and modern user experience over the bulky function-first approach that dominated spacesuit development for decades. SpaceX approached spacesuit design from the ground up, asking fundamental questions that previous engineers had accepted as solved problems. Instead of starting with existing NASA designs and making incremental improvements, they examined what astronauts actually needed to accomplish and built suits around those requirements. The company treated spacesuits as integrated components of the Dragon capsule system rather than standalone pieces of equipment that happened to connect to spacecraft. This systems-level thinking led to innovations that traditional approaches couldn't achieve because they weren't constrained by legacy design assumptions or manufacturing processes. The first major innovation lies in revolutionary pressure suit technology that eliminates the need for bulky external structures while maintaining complete life support functionality. Traditional space suits achieve pressure integrity through rigid shells and thick insulation layers that make astronauts look inflated. SpaceX developed fabric-based materials that remain soft and flexible until pressurized, then become rigid enough to maintain structural integrity against the vacuum of space. This approach allows the suit to conform closely to the astronaut's body while providing the same protection as much bulkier designs. The pressure regulation system uses advanced sensors and automated controls that maintain optimal conditions without the manual adjustments required by older suits, automatically adjusting for different activity levels and environmental conditions. The second breakthrough involves the integrated heads-up display system built directly into the helmet visor. This transparent screen provides critical telemetry without obstructing the astronaut's vision, showing pressure readings, temperature data, relative humidity levels, and communication status directly in the astronaut's field of view. The information appears overlaid on the real world rather than requiring astronauts to look down at separate instruments or rely on audio feedback from mission control. The visor incorporates indium tin oxide and copper coatings that reflect sunlight away from the crew while reflecting infrared heat back toward the astronaut when facing deep space. This coating technology, validated during SpaceX's Polaris missions, eliminates glare problems that plagued earlier helmet designs while providing superior thermal management. SpaceX EVA suits use hip-mounted power and data umbilical connections for life support rather than the backpack-mounted primary life support systems used by NASA suits. These umbilical connections provide power, oxygen, carbon dioxide removal, and communication links directly from the Dragon capsule, allowing extended EVA durations without the weight and complexity of independent life support backpacks. The hip-mounted approach distributes weight more effectively and provides easier access for connection and disconnection procedures. This umbilical system enables the suits to function as extensions of the spacecraft itself, sharing resources and data in real time while providing redundant safety pathways through multiple independent connections. Integration with Dragon capsule systems represents the most significant departure from traditional suit design philosophy. Unlike previous suits that operated as independent units, SpaceX suits function seamlessly with the spacecraft's life support, communication, and power systems. This integration enables longer mission durations and more complex operations because the suits can draw on the spacecraft's larger life support capacity when needed. The suits connect to the capsule through multiple redundant pathways that ensure astronaut safety even if individual connections fail. Balancing style with functionality required developing new materials and manufacturing techniques that hadn't been used in space suit construction before. The outer layer uses fabric-based materials interspersed with joints that provide flexibility in pressurized conditions while maintaining comfort when unpressurized. This material approach allows the suit to function effectively during launch, in-flight operations, and spacewalks without requiring different configurations for different mission phases. Advanced manufacturing techniques include in-house development of specialized fabrics and joint mechanisms that enable mass production rather than the custom fabrication required for traditional suits. Touchscreen-compatible gloves represent another significant breakthrough in spacesuit interface technology. Traditional spacesuit gloves make operating modern touchscreen interfaces nearly impossible, forcing astronauts to rely on physical buttons and switches for all interactions. SpaceX developed glove materials and designs that maintain the electrical conductivity needed for touchscreen operation while providing pressure integrity and protection against space hazards. Enhanced flexibility and tactile feedback enable astronauts to perform delicate operations with precision that traditional bulky gloves couldn't provide. The minimalist approach initially created skepticism because it appeared to sacrifice the robust, over-engineered safety margins that characterized previous spacesuit designs. However, SpaceX demonstrated that advanced materials and smart engineering could achieve superior performance in a more compact package. The suits incorporate multiple layers of protection against micrometeorite impacts, thermal extremes, and pressure loss while maintaining the flexibility needed for complex operations. Redundant safety systems built into the streamlined design provide backup protection that equals or exceeds traditional suits through multiple independent pathways and advanced monitoring systems that detect problems earlier than previous designs. SpaceX's design philosophy influences the entire space industry's approach to suit development, with other companies and space agencies adopting similar integrated approaches that treat suits as spacecraft components rather than standalone equipment. But regardless of how sleek or sophisticated these suits appear on the outside, they're true. Engineering marvel lies in the invisible systems working life support systems, your personal atmosphere. Each component works together to create a complete atmospheric system that transforms astronauts into walking planets, carrying a perfect replica of Earth's environment wherever they go in the most lethal conditions humans have ever encountered. Inside each suit, engineering systems recreate the exact conditions your body expects. 21% oxygen, comfortable temperatures around 70 degrees Fahrenheit, and precise humidity levels that keep your skin from drying out or becoming waterlogged. These portable atmospheres must function flawlessly while exposed to temperature swings of 500 degrees, deadly radiation, and a complete absence of air pressure that would kill you in seconds. Modern life support systems manage atmospheric composition with precision that exceeds what most buildings achieve on Earth. Oxygen supply systems deliver breathing gas at exactly the right pressure and flow rate to match your metabolic needs during different activity levels. When you're working hard during a spacewalk, sensors detect increased carbon dioxide production and automatically boost oxygen flow while increasing the rate of CO2 removal. During rest periods, the system reduces flow rates to conserve resources while maintaining perfect atmospheric balance. These adjustments happen continuously without any input from the astronaut, who can focus entirely on mission tasks rather than life support management. Carbon dioxide removal represents one of the most critical functions because CO2 becomes toxic at concentrations above 4%. Modern suits use CO2 scrubbing systems similar to NASA ISS EMUs but updated for smaller form factors and improved efficiency. NASA partnered with Corsians to enhance carbon dioxide monitoring inside next-generation spacesuits using advanced capnography modules. These systems monitor CO2 levels in real time while reducing helmet noise and airflow requirements, making the suits safer, more comfortable, and energy efficient. Temperature regulation requires sophisticated thermal management systems that handle heat loads from both internal body heat and external environmental conditions. Astronauts wear special cooling garments made of stretchy spandex material with chilled water flowing through about 300 feet of tubes woven throughout the fabric. This tight-fitting undergarment connects directly to the suit's life support backpack, which contains water tanks, pumps, and temperature control systems that maintain optimal thermal conditions throughout extended spacewalks by regulating body temperature and removing excess heat generated by physical activity. Humidity control prevents the dangerous buildup of moisture that could fog helmet visors or create condensation that interferes with breathing systems. Sensors throughout the suit monitor relative humidity levels and automatically adjust ventilation rates to maintain comfortable conditions. The system removes excess moisture from exhaled breath while preventing the air from becoming too dry, which could cause respiratory irritation during long EVAs. This moisture management becomes particularly challenging during high activity periods when astronauts generate significant amounts of water vapor through breathing and perspiration. Sophisticated sensors distributed throughout the suit constantly monitor atmospheric conditions and astronaut health parameters. Oxygen partial pressure sensors ensure breathing gas remains within safe limits, while pressure transducers verify suit integrity against vacuum exposure. Temperature sensors at multiple locations track thermal conditions throughout the suit environment, detecting hot spots or cold zones that could indicate system problems. These monitoring systems provide real-time data to both the astronaut and mission control, enabling immediate response to any anomalies that could threaten safety. Automated control systems process sensor data and make thousands of micro adjustments per hour to maintain optimal conditions. Computer-controlled valves regulate gas flow rates, Pumps adjust cooling water circulation, and fans modify ventilation patterns based on current requirements. These systems incorporate machine learning algorithms that adapt to individual astronaut physiology and activity patterns, optimizing performance for each crew member's specific needs. The automation reduces mental workload on astronauts while providing more precise control than manual systems could achieve. Backup systems ensure survival even when primary life support components fail because redundancy is essential when failure means death. Secondary oxygen supplies provide emergency breathing gas if main tanks develop leaks or valves malfunction. Backup carbon dioxide scrubbers automatically activate if primary removal systems become saturated or damaged. Emergency cooling systems can maintain thermal control even if main water pumps fail or cooling loops develop blockages. These redundant systems operate independently of primary systems, ensuring that single-point failures cannot compromise astronaut safety during critical operations. The complex chemistry involved in maintaining livable atmospheres requires managing multiple simultaneous chemical reactions and phase changes. Oxygen generation systems use chemical reactions or electrolysis to produce breathing gas from stored compounds or water. Water recovery systems extract moisture from the atmosphere and purify it for cooling system use. These chemical processes must function reliably in zero gravity, where normal fluid behavior and mixing patterns don't apply, while handling byproducts of human metabolism including trace gases, skin particles, and other biological waste products that accumulate in sealed environments. Extended mission capability requires life support systems that can operate independently for 8 hours or more without external support or maintenance. The XEMU incorporates advanced life support systems that enable the longer surface operations required for lunar base construction and scientific research missions through efficient resource management, high-capacity consumables, and reliable mechanical systems that require no intervention during normal operations. These life support advances enable spacewalks lasting longer and involving more complex tasks than ever before, with current EVAs routinely exceeding 7 hours and some missions pushing toward 8-hour durations. Enhanced life support reliability allows astronauts to focus on complex scientific experiments, construction tasks, and maintenance operations without constant concern about system failures. However, even the most sophisticated life support system becomes useless if astronauts can't move effectively to perform the work these systems are designed to support. Mobility breakthroughs. Moving like a human. Advanced joint engineering has finally solved the mobility puzzle that turned astronauts into clumsy robots for decades. The breakthrough lies in constant volume bearings that reduce torque by 40%, enabling natural movement that previous suits couldn't achieve. These bearings maintain internal pressure while allowing joints to bend and flex like human anatomy, eliminating the exhausting resistance that characterized earlier designs. When astronauts can move naturally, they accomplish more work with less fatigue while reducing injury risk from awkward postures and repetitive strain. Creating flexible joints that maintain pressure integrity requires solving contradictory engineering demands. The suit must contain internal pressure that prevents organs from vaporizing while allowing enough flexibility for complex manual tasks. Traditional joints use thick, rigid materials that maintained pressure but severely limited movement, forcing astronauts to work against constant resistance. Each joint represents a potential failure point where vacuum could breach the suit's protective barrier, yet these same joints must flex thousands of times during a single spacewalk without developing stress fractures or seal failures. The XEMU incorporates precision bearings positioned at shoulders, elbows, hips, thighs, and ankles that create dramatically improved lower body mobility compared to older designs. These bearing systems use specialized lubricants and materials that function reliably in extreme temperatures while maintaining smooth operation under pressure differentials. The bearings include multiple redundant pathways that ensure continued operation even if individual components fail, representing decades of refinement based on experience from hundreds of spacewalks that revealed exactly what movements astronauts need most frequently. Advanced materials and construction techniques reduce suit bulk while improving flexibility and durability. Modern fabric-based materials with integrated joints provide greater flexibility while maintaining comfort during extended missions. These materials use fiber technologies that maintain strength and pressure integrity while allowing natural bending and stretching motions. Advanced composite materials replace heavy metal components in joint assemblies, reducing overall suit weight while improving performance through manufacturing techniques that allow precise tolerances and reliable operation. Enhanced mobility translates directly to better work performance and safety during complex operations. The XEMU design enables normal walking on lunar surfaces rather than the shuffling movement that limited Apollo crews during their sandbox training exercises, where astronauts practiced in simulated lunar conditions that revealed how suit restrictions affected their ability to navigate rough terrain. Improved hip mobility allows astronauts to kneel down stably in one motion to work close to the ground, essential for scientific research requiring ground-level sample collection and instrument deployment. Sophisticated glove designs enable precise manual dexterity through advanced materials that maintain flexibility in extreme cold while providing puncture resistance against sharp objects. Custom-fitted gloves protect hands from environmental hazards while maintaining tactile feedback that allows astronauts to feel what they're handling. The gloves include heating elements that prevent fingers from becoming numb during extended operations in shadowed regions where temperatures drop hundreds of degrees below freezing. Improved joint designs in fingers and wrists reduce hand fatigue that previously limited the duration and complexity of manual tasks. Testing programs validate mobility systems under extreme conditions through comprehensive evaluation processes. The Z1 suit demonstrated improved knee and hip movement during parabolic flight tests that simulated reduced gravity environments, proving that enhanced joint designs enable more natural locomotion in space conditions. Additional testing in extreme cold environments ensures suits can withstand harsh conditions at locations like the lunar South Pole, where future missions will operate. These validation programs identify potential problems and verify that mobility systems meet performance requirements before astronauts depend on them for survival. Better mobility enables more efficient use of limited EVA time, allowing crews to accomplish more scientific research, construction work, and maintenance activities during each mission. The improved range of motion reduces injury risk by eliminating awkward postures while enabling faster emergency responses when astronauts need to quickly return to spacecraft or assist crew members in distress. Enhanced mobility allows astronauts to reach tools, equipment, and work areas that were previously inaccessible, while enabling them to climb over obstacles, navigate rough terrain, and position themselves optimally for photography and documentation tasks. These mobility advances open exploration possibilities that were previously impossible, enabling longer missions with more complex objectives requiring extensive surface operations and detailed scientific work. Astronauts can now perform tasks that demand precise coordination and strength while maintaining the flexibility needed for scientific research, equipment maintenance, and construction activities. The transformation from mechanical constraint to human-like mobility represents a fundamental shift in space exploration capability, allowing astronauts to work more like they would on Earth rather than fighting against their protective equipment. Modern spacesuits have evolved from simple pressure vessels into sophisticated systems that enhance rather than restrict human capability. But the next revolution in spacesuit technology goes far beyond mechanical improvements to create something that would have seemed like science fiction just a few years ago. Smart fabrics and AI integration. Spacesuits now incorporate smart fabrics that transform protective equipment into intelligent monitoring systems. These advanced textiles continuously track astronaut health and suit performance through sensors woven directly into the fabric itself. The integration represents a fundamental shift from passive protection to active health and safety management that provides real-time data to both crew members and mission control. Smart fabrics embedded throughout modern suits monitor astronaut health parameters with medical-grade precision. Sensors woven directly into the fabric track heart rate, blood pressure, respiratory rate, and body temperature without requiring separate monitoring equipment that could fail or interfere with suit operations. The fabric can detect changes in skin conductivity that indicate stress levels, dehydration, or fatigue before astronauts consciously recognize these conditions themselves. Temperature sensors distributed throughout the suit fabric create thermal maps that reveal hot spots or cold zones that could indicate circulation problems or equipment malfunctions. These health monitoring systems provide early warning of medical emergencies that could incapacitate astronauts during critical operations. The smart fabrics can detect irregular heartbeats, dangerous blood pressure spikes, or signs of heat exhaustion before these conditions become life-threatening. Advanced algorithms analyze patterns in vital signs to predict when astronauts might need rest breaks or medical intervention. The continuous monitoring enables mission control to track crew health status in real time and make informed decisions about mission duration and task assignments. NASA's collaboration with Corcience has enhanced carbon dioxide monitoring inside next-generation spacesuits using advanced capnography modules embedded directly into smart fabric systems. These sensors provide continuous CO2 level monitoring while reducing helmet noise and airflow requirements, making the suits safer and more energy efficient. The embedded capnography represents a significant advancement over traditional monitoring systems by integrating seamlessly with the suit's fabric structure rather than requiring separate equipment that adds weight and complexity. Suit integrity monitoring through smart fabrics represents a breakthrough in detecting structural problems before they become catastrophic failures. Microscopic sensors embedded in the suit's pressure-bearing layers can detect stress fractures, seal degradation, or material fatigue that could lead to dangerous pressure losses. The fabric sensors monitor pressure distribution throughout the suit, identifying areas experiencing abnormal stress that might indicate impending failures. These systems can detect micrometeorite impacts or punctures that create tiny holes, alerting astronauts to problems while they still have time to implement emergency procedures. Structural health monitoring sensors integrated into glove systems provide critical feedback about the most vulnerable components of spacesuits. Gloves experience the highest stress and wear during spacewalks because astronauts use their hands for virtually every task. Smart sensors embedded in glove materials track stress patterns, detect developing tears or punctures, and monitor joint where that could compromise pressure integrity. These monitoring systems alert astronauts to glove problems before they become dangerous, enabling preventive action or emergency procedures to maintain safety during critical operations. Environmental condition monitoring through fabric sensors provides detailed information about external conditions that affect suit performance and astronaut safety. Temperature sensors throughout the outer fabric layers track thermal loads from solar radiation and identify dangerous temperature gradients that could damage suit components. Radiation detectors woven into the fabric monitor cosmic ray exposure and solar particle events that pose health risks during extended missions. Humidity sensors track moisture levels that could affect suit performance or create uncomfortable conditions during long spacewalks. Machine learning algorithms integrated into NASA's primary life support system control loops analyze sensor data to optimize suit performance automatically. These systems process thousands of data points per second, identifying patterns that indicate developing problems with life support systems, mobility components, or structural integrity. The algorithms learn from operational data collected during actual missions, continuously improving their ability to predict and prevent failures. The machine learning can recognize subtle changes in system performance that human operators might miss, providing early warnings that enable preventive action. Real-time feedback systems provide both astronauts and mission control with instant access to comprehensive suit status information. Smart fabric sensors feed data to processing systems that generate immediate alerts about any conditions requiring attention. The systems can distinguish between minor variations in normal operation and significant problems that require immediate response. Mission control receives the same real-time data that astronauts see, enabling coordinated responses to emergencies and informed decision-making about mission continuation or abort procedures. Data collection systems built into smart fabrics gather information that advances spacesuit technology for future missions. Every spacewalk generates thousands of data points about suit performance, environmental conditions, and astronaut physiology that inform design improvements. The comprehensive data collection enables engineers to identify design weaknesses, validate performance models, and develop better solutions for future suit generations. This continuous feedback loop between operational experience and design improvement accelerates the pace of technological advancement. Smart systems reduce mental workload during complex tasks by handling routine monitoring and management functions automatically. Astronauts can focus entirely on scientific experiments, construction activities, or emergency procedures without constantly checking suit status or making manual adjustments. The systems provide relevant information when needed while filtering out routine data that would otherwise create distractions. This reduction in cognitive load improves astronaut performance and reduces the risk of errors caused by divided attention during critical operations. These intelligent monitoring capabilities represent just one aspect of how modern suits have evolved beyond simple protection into sophisticated systems that enhance every aspect of astronaut operations, including the fundamental ability to stay connected with their teams and mission control throughout the most challenging environments humans have ever encountered. Communication. Revolution. Staying connected. Modern space suits function as sophisticated communication command centers that manage voice, data, video, and telemetry simultaneously across multiple channels and frequencies. These integrated networks coordinate communications between individual astronauts, spacecraft systems, ground control, and backup networks without requiring astronauts to manually switch between different devices or manage complex routing decisions. This transformation from simple radio systems to comprehensive communication hubs represents one of the most dramatic advances in spacesuit technology. Integrated communication systems eliminate the traditional Snoopy cap headgear that astronauts wore for decades inside their helmets. The XEMU suits designed for the Artemis program feature a new audio system built directly into the helmet structure, ensuring consistent audio quality regardless of head position or movement during complex tasks. Previous suits required separate headsets with foam earpieces and microphone booms that could shift during movement, creating dead zones where astronauts couldn't hear or be heard clearly. The integrated communication system includes speakers mounted inside the helmet and several embedded voice-activated microphones that automatically pick up when an astronaut is talking to mission control or crewmates. These voice-activated systems distinguish between intentional communication and background noise, breathing sounds, or casual conversation that shouldn't be transmitted. The microphones use advanced noise cancellation technology that filters out the constant hum of life support systems, fan noise, and other mechanical sounds that would otherwise interfere with clear communication. Multiple microphones provide redundancy and enable the system to maintain clear audio even if individual components fail. Advanced audio systems provide crystal clear communication despite the challenging acoustic environment inside pressurized suits. Space suits create noisy environments filled with the constant sounds of fans, pumps, motors, and airflow that can overwhelm traditional communication systems. Modern audio processing uses digital signal processing algorithms that automatically adjust volume levels, filter background noise, and enhance speech clarity in real time. The systems can distinguish between different types of sounds and prioritize human voice frequencies while suppressing mechanical noise that would make communication difficult. The helmet design provides improved acoustic isolation that enhances communication quality while reducing fatigue from constant noise exposure. Better sealing around the neck and improved internal padding reduce external noise intrusion while creating more controlled acoustic environments inside the helmet. The audio systems use directional speakers that focus sound toward the astronaut's ears rather than filling the entire helmet volume with audio. This targeted approach reduces overall noise levels while improving speech intelligibility during extended missions. Modern suits integrate simultaneously with multiple communication networks that operate on different frequencies and protocols. Astronauts can maintain contact with their immediate crew members through short-range radio links while simultaneously communicating with spacecraft systems and ground control through separate channels. The suits automatically manage these multiple connections, routing communications to appropriate destinations based on content and priority levels. Emergency communications receive automatic priority routing that overrides routine traffic and ensures critical messages reach their destinations immediately. The communication systems work seamlessly across different spacecraft designs and space agencies that use incompatible radio protocols and frequencies. International Space Station operations require suits that can communicate with Russian, American, European, and Japanese systems simultaneously. The suits include software-defined radios that can be reconfigured to work with different communication standards without requiring hardware changes. This flexibility enables crew members from different countries to work together effectively while maintaining contact with their respective ground control centers. Heads-up displays integrated into helmet visors provide visual communication capabilities that supplement traditional audio systems. These transparent displays show text messages, system status information, and navigation data directly in the astronaut's field of view without requiring them to look away from their work. The displays can show communications from multiple sources simultaneously, using different colors and positioning to distinguish between routine updates and urgent messages. Augmented reality features overlaid digital information onto the real world, providing context-sensitive data about objects and equipment in the astronaut's environment. Backup communication systems ensure astronauts never become completely isolated from safety networks, even when primary systems experience failures. Secondary radio systems operate on different frequencies and power sources, providing redundant pathways for emergency communications. The suits include emergency beacon systems that automatically activate if life support or communication systems detect dangerous conditions. These backup systems can operate independently of main suit power, using dedicated batteries that provide several hours of emergency communication capability. Emergency communication protocols automatically route distress signals to multiple destinations simultaneously, ensuring that help requests reach ground control, nearby crew members, and spacecraft systems even if individual communication paths fail. The backup systems include automated distress messaging that transmits astronaut identification, location data, and basic telemetry even if the crew member becomes incapacitated. The increased activity in space operations drives the need for these advanced communication systems. NASA's current astronaut corps includes 46 active astronauts representing unprecedented diversity in backgrounds and expertise, with commercial crew programs bringing additional complexity to communication requirements. The year 2025 saw over 200 EVA hours, double the 2018 figure, reflecting the growing scope and complexity of space operations. Since the International Space Station's assembly began, astronauts have completed 248 EVAs, each requiring flawless communication systems to ensure mission success and crew safety. Better communication directly improves safety and mission success by enabling faster response to emergencies and more effective coordination during complex operations. Clear, reliable communication allows ground control to provide real-time guidance during challenging tasks and enables crew members to coordinate their activities more effectively. Enhanced communication also reduces the psychological stress of isolation that can affect astronaut performance during long missions far from Earth. Next-generation communication features will transform how astronauts work by enabling real-time collaboration with experts on Earth and other crew members across vast distances. Upcoming systems will support high-definition video streaming, three-dimensional mapping data, and interactive augmented reality that connects astronauts with remote technical support teams. These advanced capabilities will enable complex operations that require expertise not available among the immediate crew members. However, even the most sophisticated communication systems and life support technologies cannot address every challenge that astronauts face during extended operations in space. Some engineering problems require solutions that push the boundaries of what's considered acceptable to discuss in polite. The uncomfortable truth: waste management solutions. Astronauts face biological realities that require engineering solutions most people never consider. Human beings need to urinate and defecate during long spacewalks, and these basic biological functions become serious engineering problems when you're sealed inside a pressurized suit for 8 hours in the vacuum of space. The reality is that astronauts cannot simply hold it during extended EVAs, and suit designers must create systems that handle waste products while maintaining hygiene, comfort, and the psychological well-being of highly trained professionals who deserve dignity even in the most extreme environments. Waste management systems have transformed from embarrassingly crude solutions to sophisticated processing technologies that integrate seamlessly with modern life support systems. Early space programs used basic collection methods that were uncomfortable, unreliable, and often created health problems during extended missions. Astronauts in the Mercury and Gemini programs faced humiliating situations when simple collection devices failed or leaked during critical mission phases. These early failures taught engineers that waste management couldn't be an afterthought, but required the same level of engineering attention as life support and mobility systems. Modern spacesuits incorporate maximum absorbency garments that function as sophisticated adult diapers designed specifically for space operations. These mags represent advanced materials engineering that creates highly absorbent, lightweight systems that can handle liquid waste while maintaining comfort during extended physical activity. The garments use super-absorbent polymer materials that can hold significant amounts of liquid without creating bulk or weight that would interfere with suit mobility. These materials convert liquid waste into gel-like substances that reduce odor and prevent leakage that could contaminate other suit systems. The engineering challenges of creating effective waste management in sealed environments extend far beyond simple collection methods. Waste products generate heat, moisture, and chemical compounds that could interfere with life support systems or create health hazards during extended exposure. The systems must prevent bacterial growth that could cause infections or create toxic gas buildup inside the suit. Modern designs incorporate antimicrobial treatments and materials that prevent dangerous microorganism growth while maintaining skin health during extended contact with waste products. Solid waste management presents even greater challenges because astronauts cannot access toilet facilities during spacewalks that can last 8 hours or more. The maximum absorbency garments handle solid waste through containment systems that isolate waste products from the astronaut's skin while preventing contamination of other suit components. These systems use barrier materials and odor control technologies that maintain bearable conditions inside the suit during extended operations. The waste management systems must function reliably regardless of body position or movement patterns that could shift waste materials within the garment. Integration with life support and monitoring systems requires careful attention to how waste management affects other suit functions. Waste products generate moisture that must be managed by humidity control systems to prevent dangerous condensation buildup. The systems must account for the additional heat generated by waste decomposition and bacterial activity that could overwhelm thermal regulation systems. Modern suits include sensors that monitor conditions within waste management systems, alerting astronauts and mission control to potential problems before they become health hazards or equipment failures. Self-healing polymers represent the next breakthrough in waste management materials, using phase change capsules embedded within the fabric structure that automatically seal minor tears or punctures that could compromise containment systems. These microscopic capsules contain healing agents that activate when the material experiences damage, flowing into gaps and hardening to restore barrier integrity. The phase change technology responds to temperature variations and mechanical stress, providing automatic repair capabilities that maintain system performance throughout extended missions without requiring astronaut intervention or replacement procedures. Advanced fabric technologies incorporate antimicrobial treatments that prevent bacterial growth and reduce odor production during extended missions. These treatments must remain effective throughout the duration of long spacewalks while avoiding chemical reactions that could irritate skin or create toxic compounds in the sealed suit environment. The materials must also be compatible with other suit systems, avoiding chemical interactions that could damage seals, electronics, or life support components. Testing and validation of waste management systems requires procedures that maintain astronaut dignity while ensuring reliable performance under extreme conditions. Engineers must verify that systems can handle the full range of human waste products while maintaining comfort and hygiene standards. Testing protocols simulate the physical stresses of spacewalks, including the effects of microgravity, pressure changes, and extended physical activity on waste management system performance. Closed-loop life support systems for future deep space missions will incorporate waste processing technologies that recycle human waste products into useful resources. These systems adapt cabin-based oxygen production technologies for integration into portable life support backpacks, enabling suits to process waste materials and extract water, oxygen, and other consumables during extended surface operations. The closed-loop approach reduces the mass of consumables that must be carried during long missions while providing backup resources that enhance crew survival capabilities during emergencies. Improved waste management systems directly enable longer and more complex missions by removing biological limitations that previously constrained EVA duration. Early spacewalks were limited partly by the inadequacy of waste management systems that became uncomfortable or unsanitary during extended operations. Modern systems allow astronauts to work for 8 hours or more without significant discomfort or health risks from waste accumulation. This capability becomes essential for lunar surface operations and future planetary missions where extended EVAs will be necessary for construction, scientific research, and maintenance activities. These advances remove major limitations on mission complexity by ensuring that astronauts can perform demanding physical tasks without the distraction or discomfort of inadequate waste management. The psychological benefits of reliable, dignified waste management systems contribute to overall mission success by maintaining crew morale and focus during challenging operations. Current waste management technology represents a foundation for even more advanced systems required for future missions where astronauts may spend extended periods in space suits during planetary surface operations. The unglamorous engineering behind these systems enables the remarkable achievements that define modern space exploration, supporting mission complexity and duration that would have been impossible with earlier technology. 2025 Space Statistics, the current reality. These engineering breakthroughs translate into operational statistics that reveal the true scale of modern space exploration. NASA's current astronaut corps comprises 46 active astronauts, including 19 women and 27 men, representing the most diverse group of space explorers ever assembled. This relatively small number contrasts with the peak of 2000 when NASA maintained 149 active astronauts, but today's crews are supported by commercial astronauts from SpaceX, Blue Origin, and other private companies that have fundamentally changed how we staff space missions. The total number of humans qualified for space operations has actually increased when you include commercial crew members and international partners working on joint missions. Extravehicular activity statistics for 2025 demonstrate the incredible pace of spacewalk operations across multiple programs and platforms. NASA logged over 200 EVA hours this year alone, more than double the spacewalk time recorded just 5 years ago. The International Space Station has hosted 248 spacewalks since assembly began, with current operations maintaining an average of 1 EVA every 3 weeks. These spacewalks routinely exceed 7 hours in duration, with the longest 2025 EVA lasting 8.7 hours during critical station maintenance operations. The success rate for planned EVAs remains above 98%, demonstrating the reliability of current spacesuit technology and crew training programs. Spacesuit performance data reveals reliability statistics that would be impressive for any complex mechanical system operating in extreme environments. Current generation suits maintain pressure integrity through more than 99% of operational time, with no catastrophic failures recorded during the past 3 years of intensive operations. The suits demonstrate mean time between failures of over 300 operational hours, significantly exceeding the performance of earlier generations. Battery life has improved to support 8-hour EVAs with adequate reserves for emergency situations, while life support systems consistently maintain optimal atmospheric conditions throughout extended operations. Mission complexity in 2025 far exceeds anything attempted during the early decades of space exploration. Today's EVAs involve simultaneous coordination between multiple crew members, spacecraft systems, and ground control centers across different time zones and countries. Astronauts routinely perform tasks that require precise manual dexterity, complex tool operation, and coordination with robotic systems during single spacewalks. The scientific instruments deployed and maintained during current EVAs represent technology that didn't exist during the Apollo era, requiring spacesuits that can accommodate touchscreen interfaces, delicate electronics, and sophisticated measurement equipment. Current spacewalks support construction projects that are building the infrastructure for permanent human presence in space. The International Space Station continues expanding with new modules and external platforms that require extensive EVA support for installation and maintenance. Lunar Gateway program preparations involve testing procedures and equipment that will enable sustained operations at the Moon. These construction activities demand spacesuits that can handle extended exposure to space environments while providing the mobility and dexterity needed for complex assembly tasks. Commercial space industry growth has created unprecedented demand for spacesuit technology across multiple platforms and mission profiles. SpaceX has conducted numerous crewed missions carrying both NASA astronauts and commercial crew members who require suit systems compatible with Dragon capsule operations. Blue Origin's suborbital flights are testing spacesuit designs for tourist operations that will eventually require mass production capabilities. Private space stations under development by Axiom Space and other companies will need suits designed for commercial operations rather than traditional government missions. The commercial sector has introduced rapid development cycles that contrast sharply with traditional space agency timelines. Companies are designing, testing, and manufacturing space suits in time frames measured in years rather than decades. This acceleration has pushed innovation in material science, manufacturing techniques, and system integration approaches. Commercial demand for space suits is driving cost reduction efforts that make space operations more economically viable, while maintaining the safety standards required for human spaceflight. International cooperation statistics demonstrate the global nature of current space operations. The International Space Station hosts crew members from 17 different countries who must work together using compatible equipment and procedures. European Space Agency astronauts use NASA space suits during EVAs, while Russian cosmonauts operate their own Orlan suits for station maintenance activities. This international cooperation requires standardized interfaces and communication protocols that enable seamless integration between different national space programs. Joint missions between multiple space agencies have become routine rather than exceptional events. The Artemis program includes partners from Canada, Europe, Japan, and other countries who will contribute both crew members and equipment to lunar operations. These international partnerships require spacesuits that can accommodate astronauts from different countries while meeting the safety standards of all participating agencies. The coordination required for these multinational missions exceeds anything attempted during the Cold War era when space programs operated in isolation. Current trends indicate that spacesuit requirements will continue expanding as exploration activities extend beyond Earth orbit. Lunar surface operations plan for the next few years will expose suits to environmental conditions not experienced since the Apollo program ended over 50 years ago. The suits must handle abrasive lunar dust, extreme temperature cycles, and extended surface operations lasting weeks rather than days. Mars mission planning requires suits capable of functioning reliably for months or years with minimal maintenance or replacement opportunities. The pace of technological advancement in spacesuit systems has accelerated dramatically over the past 5 years. Artificial intelligence integration, smart fabric development, and advanced life support systems are being developed and tested on timelines that would have been impossible under traditional development approaches. This rapid innovation cycle is driven by the increasing frequency of space operations and the growing number of organizations involved in human spaceflight activities. These statistics reveal humanity's remarkable progress in making space exploration routine rather than exceptional, but the engineering challenges ahead dwarf everything accomplished so far. The future of spacesuits beyond 2025. Spacesuit engineers are developing technologies that would have been pure science fiction just a decade ago. Self-repairing materials represent one of the most promising breakthroughs, using polymer chemistry that allows suit fabrics to automatically seal minor punctures and tears without human intervention. These smart polymers contain microscopic capsules filled with healing compounds that rupture when the material suffers damage, releasing chemicals that bond together and restore structural integrity within minutes. The technology draws inspiration from biological healing processes, creating synthetic materials that can recover from damage just like living tissue repairs itself after injury. These self-healing capabilities become essential for Mars missions where astronauts will spend months on the planetary surface with no possibility of suit replacement or major repairs. Mars presents unique hazards including dust storms with particles moving at hurricane speeds, sharp volcanic rocks that can puncture conventional materials, and temperature swings of 200 degrees that cause repeated thermal stress on suit components. Self-repairing materials must function across these extreme temperature ranges while maintaining their healing properties despite exposure to cosmic radiation and chemical reactions with the Martian atmosphere. Mars missions will require suits that function as completely independent spacecraft capable of supporting human life for weeks at a time. Future Mars suits must include closed-loop life support systems that recycle air, water, and waste with near-perfect efficiency because resupply from Earth takes months and costs millions of dollars per kilogram. These life support systems will incorporate biological components including algae bioreactors that consume carbon dioxide and produce oxygen, bacterial waste processing systems that break down human waste into useful compounds, and water recovery systems that purify and recycle every drop of moisture from breathing, perspiration, and waste products. The closed-loop systems present engineering challenges that exceed anything attempted in current spacesuits. The biological components must remain stable and productive despite cosmic radiation exposure that would kill most Earth organisms. The recycling systems must operate reliably for months without maintenance or replacement parts while handling the full spectrum of human metabolic byproducts. These systems will incorporate multiple redundant pathways and backup processing methods to ensure astronaut survival even when individual components fail or become contaminated. Artificial intelligence integration in future suits will transform them into intelligent systems that monitor, predict, and respond to changing conditions faster than human reflexes can manage. Advanced AI systems will continuously analyze thousands of sensor inputs to predict equipment failures, health emergencies, and environmental hazards before they become dangerous. These AI systems will learn individual astronaut physiological patterns and behavioral preferences, optimizing suit performance for each crew member's specific needs and work habits. Machine learning algorithms will process data from suit sensors, astronaut biometrics, and environmental conditions to identify subtle patterns that indicate developing problems. The AI will predict when life support components need maintenance, when astronauts require rest breaks, and when environmental conditions might become hazardous. These predictive capabilities will enable proactive responses that prevent emergencies rather than simply reacting to problems after they occur. Enhanced mobility systems under development will finally eliminate the movement restrictions that have frustrated astronauts for decades. New joint designs use advanced bearing systems and flexible materials that provide natural human range of motion while maintaining perfect pressure integrity. These mobility improvements will enable astronauts to run, jump, and climb across planetary surfaces with confidence and efficiency that matches their Earthbound capabilities. The mobility advances incorporate lessons learned from robotics research and prosthetic development, using technologies originally designed for artificial limbs and industrial automation. Advanced actuators and sensor systems will provide powered assistance for heavy lifting and repetitive tasks while maintaining the natural feel of unassisted movement. These powered mobility systems will enable astronauts to carry heavier equipment loads and work longer hours without the fatigue that currently limits EVA duration and productivity. Future manufacturing techniques will revolutionize how spacesuits are designed, produced, and customized for individual astronauts. Three-dimensional printing technologies will enable on-demand production of suit components using materials available on Mars, the Moon, or asteroid mining operations. This manufacturing capability will reduce dependence on Earth-based supply chains while enabling rapid customization and repair of suit systems using local resources. Advanced manufacturing will also enable completely new suit architectures that current production methods cannot achieve. Integrated electronics, embedded sensors, and complex internal structures will be printed as single components rather than assembled from separate parts. This integrated manufacturing approach will create lighter, stronger, and more reliable suits while reducing the number of potential failure points that could compromise astronaut safety. Adaptive suit systems will automatically reconfigure themselves for different environments and mission requirements without requiring manual adjustments or component swapping. Shape memory materials will allow suits to change their profile and characteristics based on operational needs, becoming more flexible for scientific work or more protective during hazardous activities. These adaptive systems will incorporate multiple operational modes optimized for different environments, including vacuum, planetary atmospheres, underwater operations, and high radiation zones. The next decade will likely produce space suit advances that exceed everything achieved during the previous 60 years of human spaceflight. Current research projects are developing capabilities that will enable permanent human settlement of other worlds, multi-year deep space missions to asteroids and outer planet moons, and industrial operations in space that require sophisticated protective equipment. These advances will create suits that function more like wearable spacecraft than protective clothing, providing astronauts with the tools and capabilities needed to establish thriving human communities throughout the solar system. These technological achievements represent more than just engineering progress. They embody something fundamental about human nature and our relationship with the impossible. Space suits transform engineering challenges into exploration opportunities, proving that technical innovation can overcome the most hostile environments in the universe. These systems work because thousands of engineers dedicated their careers to solving problems that seemed impossible, turning science fiction concepts into reliable hardware that protects astronauts millions of miles from home. Every component represents decades of learning from failures, near misses, and the constant refinement of technology where anything less than perfection means death. The suits enabling today's missions are preparing us for tomorrow's destinations. Mars awaits, along with asteroids, distant moons, and places we haven't even imagined yet.